In order to find a maximum flow for a graph network, we'll initially assign a flow of 0 to every edge and then repeatedly find an augmenting path. An augmenting path will be a path along which flow could travel. It will be precisely where we can increase by some amount along edges of this path the flow in order to increase the flow of the entire network in such a way that we still satisfy the conservation and capacity rules. Now, the amount of flow which can be increased along this augmenting path is called the residual capacity. So we can define residual capacity for an edge as follows. So we have for some edge, which is directed from U to vertex V, the residual capacity from U to V, if we were to follow this along the forward direction, is how much more additional flow we could send. We're already sending this much flow through that edge, and that edge has capacity this. So the residual capacity is just how much more we could send through this edge from U to V without violating the capacity rule. Now, the residual capacity of this edge, if we were to follow it kind of going back to send through this edge, but from V to U, is how much flow we were already sending through that edge. So in the first case, we're considering going from U to V. In the second case, we're considering going from V to U. And this would be how much flow we can send back from V back to U. And this is just however much we were already sending from U to V. So the residual capacity of a path is just the smallest residual capacity along all of the edges of that path in the direction from S to T. So for example, I have here a path highlighted in blue. It goes from, here's S, we have an edge to U, from U we have an edge to W, we had an edge to W also from V, and then an edge from V to T. So here's an example of a path that connects S and T. Now notice that we don't need that all edges are going the same direction. So this is why we have a different definition of residual capacity depending on which direction we're effectively sending flow through. Now, here we could say this is if I want to distinguish them as forward edges or back edges in this way, I have a forward edge here, a forward edge here, back edge here, and a forward edge here. So the residual capacity of S to U is 3 because we could send an additional 3 units of flow through this without maxing out this, let's say, 5 gallons capacity. From U to W, its residual capacity is 1. From W to V, because we're already sending 1 unit of flow through this, then from W to V we could send 1 unit of flow back. And from V to T, the residual capacity is 2. So the smallest value among all of these is 1. This is the residual capacity of the entire path. Now we say that a path is an augmenting path if its residual capacity is greater than 0, because this means that along that path we can augment it, we can change the flow in such a way that we increase the flow of our network. So if we have an augmenting path, call it pi. This is augmenting because the residual capacity of that path, delta pi, is greater than 0. Then there is a flow for that network which can be increased by the residual capacity of that path. And how this is accomplished by along forward edges of that path, we increase the flow by this residual capacity, and along backward edges, we decrease the flow by that residual capacity. So taking the same flow network we had from before, we identify that the residual capacity of this path is 1. So along these forward edges, we increase by 1. And along the back edges, we decrease by 1. So this is the resulting flow network that we have below. So by changing the flow along this augmenting path, we've increased the total flow of our network from 7 to 8. Okay, so I hope that the first part of this is clear, why we would increase by residual capacity. Since the residual capacity of that path is the smallest residual capacity of any edge, then we don't exceed the capacity the capacity rule, and since we're increasing it along this path, we don't violate the conservation rule either. And the only thing which might not be clear to you is where this back edge comes into play, why we're decreasing residual capacity. So let's try to better understand what it means to have a back edge in some augmenting path. So let's say we have some back edge here from, let's say, u to v. Now, and suppose this exists in some augmenting path that we have from our source, which goes to v along some path, and then from u, this eventually goes to the sink t. And we have that this is an augmenting path, so the residual capacity along each edge is greater than 0. So because the residual capacity of this edge from v to u, of this back edge, is greater than 0, then that means we were already sending flow through this network, through vertex u, which went ultimately from the source vertex somewhere to vertex u, to vertex v, and then, since we don't lose it, it ultimately went to vertex t. So because there exists a back edge in this augmenting path, then that means there exists some path, some way, where we were sending flow from the source to u, through this edge, and then from v to the sink t. Now by decreasing the flow sent from u to v along this edge, and increasing the flow along these edges where we have a forward path, in effect we're rerouting where we were sending the flow to u before. So before we were sending it from s to u, from u to v, and then from v to t. And then now that we've increased the flow along all these forward edges, and we've increased the flow along these forward edges, and we decrease the flow along this edge, we're effectively saying that instead of sending that old flow, what we had from s to u, and then u to v and v to t, instead of using this edge to get to t, that old flow will go from s to u, and then from u it will follow this path where we had increased flow to get to t. Now the new flow that we had added will go from s to v, we increase the flow along this path, and then from there it will use the old path, what we had before, where we were already sending flow from v to t. It'll use that same path. Alright, so Ford-Fulkerson's algorithm is an approach to finding a maximum flow in a graph exactly by finding these augmenting paths, and as long as we still have one, it'll increase the flow along that path exactly in this way, by increasing by the residual capacity for forward edges and decreasing by the residual capacity for back edges. So this is Ford-Fulkerson's algorithm. Given a network, we'll initially set a flow value of 0 to all edges, and then it will repeatedly look for an augmenting path. Now we can modify any of the graph traversal algorithms that you've seen already, depth first search or breadth first search, in order to find an augmenting path, just by following either incoming or outgoing edges, as long as that edge along the direction in which it's traveled from has a residual capacity greater than 0. So we can compute an augmenting path that way, from the source vertex to the sink vertex. And then figure out, okay, now that we have an augmenting path, figure out the residual capacity for that path, which is just the minimum residual capacity of any edge along that path. So the first step is to compute for each edge along the path of residual capacity for that edge. So this is different based on if we have a forward edge or a back edge. And then set the residual capacity for the path as just the smallest value residual capacity for each edge. And then, now that we've computed that, change the flow of the network by changing the flow along this augmenting path, increasing by this residual capacity for forward edges, decreasing by this residual capacity for back edges. So you're going to see an example of this on an input graph in a moment, but first I want to point out that from this we already obtained that the maximum flow of a flow network is equal to the capacity of a cut, which has minimum capacity. And the reason for this is when we're finished with Ford-Fulkerson's algorithm, this occurs because there's no augmenting path from the source to the sink, because Ford-Fulkerson's algorithm will repeatedly find an augmenting path. So if we're finished, then that means there is no augmenting path. So we can define a partition of vertices as all of those vertices which we could reach along an augmenting path from the source. And we know that this doesn't include the sink, because otherwise Ford-Fulkerson's would have continued. So we'll define the remaining vertices as just everything else which we couldn't reach via an augmenting path. We know it includes the sink. So this gives us a cut, a partition of vertices. Now, the flow of this cut and of our network is the capacity of this cut, because we've maxed out all forward edges, we've sent flow along them, and any back edge has a flow of 0. So this is why we couldn't find an augmenting path. Any edge which goes from the set Vs to Vt, we've already effectively maxed out that there is no augmenting path from these vertices to any other vertex from Vt. So this means that the flow of f has maximum value and the cut has minimum capacity, giving us that the maximum flow is equal to the capacity of a minimum cut. Alright, so you'll see in the next video an example of Ford-Fulkerson's algorithm.